Hi everyone. So let me begin your next chapter, that is sequence 2. So in this let me begin to prove a theorem, that is if limit n tends to infinity an is equal to a and your a should not be equal to 0, then there exists a positive number k and a positive integer m such that modulus of an is greater than k whenever n is greater than or equal to m. So here we use the given data, that is limit n tends to infinity n is equal to a and your a should not be equal to 0. Here your k and m are positive integers. Okay, so proof for this is, since a is not equal to 0, so we take epsilon is equal to half of modulus of an, and that should be strictly greater than 0. Okay, so then here an tends to a. Okay, so here your sequence an has a limit point, that is a. So therefore there exists a positive integer m such that modulus of an minus a is less than epsilon for all n greater than or equal to m. So here we are using the definition of your convergent of a sequence. Okay, so using that we are rewriting this in the form modulus of an minus a is less than epsilon for all n greater than or equal to m. So now modulus of, here we are taking modulus of a is equal to, here I am adding an and subtracting an. So then it will become modulus of a minus an plus an. So this is equal to, so here I am arranging the terms, that is a minus an plus an. So therefore using the modulus property we are writing this as this in the form modulus of an minus a plus modulus of an. So this implies that you already know that modulus of an minus a is less than epsilon. Okay, so using that I am writing, this implies that modulus of a is less than or equal to epsilon plus modulus of an. So this implies that modulus of an is greater than modulus of a minus epsilon. So after rearranging the terms it will become modulus of an is greater than modulus of a minus epsilon. So in the beginning we have taken that your epsilon is equal to half of modulus of an. So I am writing that. So this implies that modulus of an is greater than modulus of a minus half of modulus of an. So this implies that modulus of an is greater than half of modulus of an. So for all n greater than or equal to m. Okay, so therefore we have found here a positive integer k that is equal to half of an. So here I am taking this as k, and a positive integer m, this positive integer m, such that modulus of an is greater than k1 for all n greater than or equal to m. So this result is saying if limit n tends to infinity an is equal to a and a should not be equal to 0, then there is two positive integers, that is k and m, such that your n is greater than k whenever n is greater than equal to m. So here what we are taking here, using the definition of your convergent sequence, we are taking modulus of an is less than epsilon, an minus a is less than epsilon. So using that I am rewriting the term, that is modulus of a is equal to, in this form, here adding and subtracting an. So after that what we are getting here, your modulus of a is less than or equal to epsilon plus modulus of an. So after rearranging the terms, what you are getting here, modulus of an is greater than modulus of a minus epsilon. So your epsilon we have already taken that half of modulus of an. So I am putting that value here. So then your modulus of an is greater than half of modulus of an. So I am taking this as your k. Okay, and a positive integer m such that modulus of an is greater than k. Modulus of n is greater than k for all n greater than equal to m. So this is the theorem. Okay, first theorem. So let we begin an important result, that is Cauchys first fundamental theorem on limits. Cauchys first fundamental theorem on limits. So we are using here a concept of your same convergent sequence. So using that we will prove this Cauchys first theorem on limits. So here your statement meaning is, if sequence an converges to L, then there exists a sequence an where xn is equal to a1 plus a2 plus a3 plus so on an divided by n also converges to L. So if your sequence an converges to L, then xn is equal to a1 plus a2 plus a3 plus so on divided by an also converges to L. So this statement can be rewritten as, if limit n tends to infinity an is equal to L, then prove that limit n tends to infinity a1 plus a2 plus an divided by n is equal to L. So either this or this, anyone you can write. Okay, so these are two forms. Okay, so proof for this. So here I am taking, let Bn is equal to modulus of an minus L. Let Bn is equal to modulus of an minus L. Then limit, I am taking limit n tends to infinity both sides. Then it will become limit n tends to infinity Bn is equal to limit n tends to infinity an minus. So this is a constant value, that is L. So limit n tends to infinity L means L itself. But here we are taking a sequence that is an. So limit n tends to infinity an is equal to L, because your sequence an converges to what? L. So because of that reason I am taking here limit n tends to infinity an is equal to L. So therefore I am putting this value in this equation. So it will become, therefore limit n tends to infinity Bn is equal to L. So this is L minus L. So this is equal to 0. Means limit n tends to infinity Bn is equal to 0. So that can be written as Bn tends to 0. So I am taking this as equation number 1. So now your Bn is equal to an minus L. So this implies that after rearranging this term, so you get an is equal to Bn plus L. So already you know that this can be expressed in the form of a1 plus a2 plus a3 plus so on an, and your Bn also can be written as b1 plus b2 plus b3 plus so on Bn with L. So I am writing this as, so your an plus a1 plus a2 plus a3 plus an plus so on divided by plus so on an divided by n can be written as xn. So this is equal to b1 plus L, b2 plus L, so on Bn plus L divided by n. So here I am taking b1 plus b2 plus Bn in the one form plus, so these are n times L terms, so plus nl divided by n. So after dividing it will become b1 plus b2 plus so on Bn divided by n plus L, because nl plus nl divided by n. So nl means nl get cancels, remains what? L. So in order to prove xn tends to L, it is enough to prove that b1 plus b2 plus Bn divided by n tends to 0. b1 plus b2 plus Bn divided by n tends to 0. So now from equation 1, Bn tends to 0. So because in equation 1 your Bn tends to 0, so I am using that term again. So now from 1 Bn tends to 0. So therefore given epsilon greater than 0, there exists a positive integer m. There exists a positive integer m such that modulus of Bn less than epsilon by 2 for all n greater than equal to m. So again here I am taking your Bn tends to 0, means the sequence Bn is convergent, because here the point means limit n tends to infinity Bn is equal to 0, means the sequence Bn converges to 0. Okay, so this can be rewritten as the sequence Bn is convergent. So if the sequence is convergent, then it is bounded. Okay, so this implies that the sequence Bn is bounded. So then I am rewriting, so this implies that if sequence Bn is bounded, there exists a real number m greater than 0 such that modulus of Bn is less than m for all n. So I am using the definition of your bounded sequence. Okay, so now let us prove 2, that is b1 plus b2 plus b3 plus so on bn divided by n tends to 0. So now we have to prove this. Okay, so let b1 plus b2 plus bn divided by n minus 0 is equal to because this sequence converges toward 0. So because of that, so this is equal to, so this equation can be rewritten as b1 plus b2 plus bn divided by n. I am taking modulus separately. So then it will become modulus of b1 plus b2 plus bn divided by modulus of bn. So using the property of your modulus, this can be written as this. Okay, so this is equal to 1 divided by n. So because n belongs to n means your modulus of n also becomes n. So this is equal to 1 divided by n into modulus of b1 plus b2 plus so on bm plus 1 plus so on bn. So this is less than or equal to, using the modulus property, this equation can be rewritten as like this. So 1 divided by n modulus of b1, so this is modulus of b2 plus so on modulus of bn, this is bm plus modulus of bm plus 1 plus modulus of bn. Okay, so these are m terms, these are n minus m terms. Okay, so therefore this can be rewritten as this is less than m plus me, because your bn is less than m. Okay, so here if I take m terms b1 plus b2 plus b3 plus so on bm, so these are m, so how many times? M times. Okay, so after that bn is less than what? Modulus of bn is less than epsilon by 2. Modulus of bn is less than epsilon by 2. So your bm plus term becomes epsilon by 2 plus epsilon by 2. How many times? n minus m times, because already your b1, b2 plus so on bm, these are m terms. So here your value of b1 is what? M, capital M, how many times? M times. So these are epsilon by 2, how many times? N. So these are n terms, n minus m terms. Okay, so then it will become, so this is less than 1 by n, m plus so on m times plus epsilon by 2 plus so on n minus m times, using equation 3 and 4. Using equation 3 and 4 we can write this. So this is less than, so how many times? These are m times, m into m. So your epsilon by 2, how many times? N minus m times. So small m into m plus n minus m into epsilon by 2. So this is less than m into m divided by m plus n minus m divided by n into epsilon by 2. So this can be written as m into m divided by n plus epsilon by 2, because here n minus m divided by n divided by n so this will become 1 minus m divided by n. So if you take any positive numbers, so this will be less than what? 1. So then this equation becomes m into m divided by n plus epsilon by 2. So therefore b1 plus b2 plus bn b1 plus b2 plus so on bn divided by n is less than m into m divided by n plus epsilon by 2. So now m into m divided by n is less than epsilon by 2 if n divided by m into m is greater than 2 by epsilon. So that implies that n is greater than 2 times m into m divided by epsilon. Okay, so if p is using the definition of your convergent sequence, we can write this as if p is a natural number greater than 2m divided by epsilon and q is equal to maximum of p, m and p, then b1 plus b2 plus so on bn divided by n minus 0 is less than epsilon by 2. This is also epsilon by 2 and this is also epsilon by 2. So epsilon by 2 becomes how many times? Epsilon times for all n greater than or equal to q. So this implies that using the definition of your convergent sequence, we can rewrite this in the form of like this: b1 plus b2 plus so on bn divided by n tends to 0. So from equation 2 we have xn tends to L, because your bn tends to 0 means here your b1 plus b2 plus bn divided by n tends to 0. So after putting the value in this equation, that is xn is equal to what? Your xn is b1 plus b2 plus bn divided by n plus L. So if we put the value from equation 2, if we put all these values, means b1 plus b2 plus bn divided by n tends to 0, then your xn tends to what? L. So therefore here your xn tends to L, that is a1 plus a2 plus an divided by n tends to L. So if I take limits on both sides, then it will become limit 10 means so this is of the form in the form of your convergent sequence. So after rearranging the terms, so then it will be of the form limit n tends to infinity a1 plus a2 plus so on n divided by n is equal to L. So this is the proof of your Cauchys first theorem. So if you have any doubts regarding this, so you can send your doubts through to my WhatsApp number. Thank you.